budget-friendly treadmill motor power supply shootout. Let's hook all these up to my mill one at a time and see how they perform. Greetings, fellow DIYer, and welcome to my video. So I recently did a video on this unit right here. It's a variable transformer, and when hooked to a bridge rectifier, you can use it to power a treadmill motor. At the end of that video, I alluded to an upcoming project where I will be building a small engine dyno that I can use to test performance of small engines and small electrical motors. That video got a lot of positive feedback. A lot of people are very interested in the dyno build. A lot of people were interested on how this variable transformer would compare to other budget-friendly options out there. And I realized that this dyno build could be months out. You know, I am not a full-time YouTuber. I have other responsibilities. YouTube is something that I spend a fair amount of time on, but these projects take time. Shooting video takes time, editing takes time. So it could be quite a few months before I have the dyno built and that video is up. But that leaves the question unanswered. What is the best budget-friendly option to power a treadmill motor? I got to thinking there's got to be a way that I can test this in a practical world. And I've got 3 shop tools that are powered by treadmill motors: my lathe, my mill, and my bandsaw. And at first I thought the bandsaw might be a pretty good option. I could install a dull blade, hook each type of power supply up to the bandsaw, and cut some things, see if there's a significant drop in RPMs. The problem is I'm human. And as I'm pushing work into the blade, I can't necessarily keep that pressure consistent. The second issue is I would have had to have rigged something to test RPMs on said bandsaw. In fact, with those 2 obstacles, I don't even know why the bandsaw was my first choice, because, as I said, I have a lathe and a mill that both have a treadmill motor running them. I quickly realized that my mill was a fantastic test bed because it has power feed, it has a DRO so I can set depth of cut, and I can easily get to the wires to plug in the different treadmill motor power supply options. And that is exactly what we're going to do right here. So this is what we're going to use to test for a loss in torque at various RPMs. This is my adjustable column mill. If it looks DIY, that's because it is, but that's a totally different video. Actually, it's several different videos. It's powered with an SCR voltage controller, so the first test will involve the SCR voltage controller. I have a 3/8 piece of steel in the vise. I have my cutting tooling in the mill. It's got a DRO on it, so I can set the depth of cut at exactly 10 thousandths. And then I've got an RPM meter so that we can see exactly what the RPMs start at and what they drop to as the cuts are being made. And then it's got power feed so that the drive as we're going through the piece of test steel is consistent. There's no human error of it being too fast or too slow. The process will be simple. I'm going to set the RPMs at 3 different speeds: 300, 600, and 900. That should give us a really good picture if there's less of a reduction in torque as RPMs go up. I have a feeling it's going to take a little bit to dial them in. If we're off by 1 or 2, that'll be okay, because ultimately what's going to happen is when I move this 3/8 piece of steel into the cutting blade, there should be a reduction in speed. Now, this is a Hall sensor type RPM gauge, and so it will take a minute for this to catch up. As we're making a pass, RPMs are probably going to stay pretty close to the same, and then all of a sudden they'll drop. And what I'm going to do is take the number we started at and then the lowest number that we end up getting, and we'll set up a ratio to see what percentage drop in speed we had. And that should relate directly to how much torque the motor is able to put out with any given power supply. Now, the important thing here is this mill is geared at 3.5 to 1. The treadmill motor would normally have a max speed of almost 5,000 RPMs, and its current max speed is closer to 1,500. And why that's important is if you're using a treadmill motor, most of the time you're not going to need it to scream at the max RPMs in a 1-to-1 ratio. You're going to want to gear it to maximize torque. So I just wanted to point that out, that will have an effect on this test, but the nice thing is it's the same motor, it's the same gear ratio, regardless of which power supply we are using. So this is an SCR voltage controller. If you've seen any of my other videos, you know that I'm quite fond of this as an option to power a treadmill motor. Admittedly, the power that comes out of it is not the cleanest power that you can get. There are far cleaner options than the SCR voltage controller. But when you buy a good quality SCR, there are a bunch of advantages, in my opinion, to this unit. This is what I currently have on all three of my shop tools that are being run by a treadmill motor. And this is going to be what we test first. A cut at 300 RPMs. As you can see, the drop in RPMs was really pretty insignificant using this. Most things that are powered by a treadmill motor do have a little bit of a drop in speed when a load is applied. So it's not abnormal to have a little reduction. When we started at 301 RPMs, we dropped down to 279, so 22 RPM difference. When we started at 598, we dropped down to 583, a 15 RPM reduction. And when we started at 901, we dropped down to 885, a 16 RPM reduction. Now, with numbers like 22, 15, and 16, I would say those differences are pretty negligible. In other words, I interpret that result as the same amount of drop across all three starting RPM ranges. Yes, 22 is a little more than 15 and 16, but not much. Not enough to really worry about. And that just goes to show the value of a treadmill motor. DC motors put out the same torque at full range of RPM, assuming that the power supply provides consistent amperage through full range of RPM. Now, I didn't take the motor down to super slow speeds because at super slow speeds, we're going to have cutting problems. In fact, I had cutting problems at 300 RPMs. That cutter I'm using really wants to go a whole lot faster than 300 RPM. And I know that the slower we get, then we are going to have a situation where amps drop for most power supplies. But for the case of good usable RPM, it was consistent. And to only lose 22 RPMs shows that the motor has good torque when using this unit. Now the variable transformer. The reason that I wanted to do this test as soon as I possibly could. It dropped a little more than the SCR voltage controller did, but again, not a huge amount. We started at 299 and we dropped to 257, so 42 RPMs. We started at 602 and dropped to 543, so 59 RPMs. And then we started at 895 and dropped down to 842, 53 RPMs. So again, it's very consistent. I take those three results as basically statistically the same number. Again, showing that we are at the point with this unit that amperage is going to be consistent through the full range of voltage. Now with the SCR, I was able to dial in pretty much to 1 or 2 RPMs, and that's because of the coarse speed control and fine speed control that I added to that unit. With this, it wasn't quite that accurate. It was still probably within 5 to 10 RPMs, but because the connection is moving from one coil wire to the next coil wire, there are gaps. So you have about a 5 to 10 RPM gap that you just can't quite get in between. For the kind of work that I'm doing, for the kind of work that most people are going to be doing on their lathe or mill or other things they're powering with a treadmill motor, that 5 or 10 starting RPMs isn't going to make a difference one way or another. It's not going to significantly increase chatter or affect the quality of the cuts if it's, 5 or 10 RPMs off of where you want it to be. So not as easy to dial in as the SCR, but still good enough. And last, we have the MC-2100 and corresponding pulse width modulator signal generator to control it. This was an interesting unit to test because I had some somewhat anomalous readings. And I think it has to do with the other components on this. Being that this is designed to drive a treadmill, it has components built into it to try and maintain speed. So we started at 323. Now that's significantly faster. Well, not significantly, but it is faster than the 300 RPM that I was shooting for with the other two units. And the problem is that's as close as I could get. This pulse width modulator has 100 speed options. You go from 0 to 100 in 1% steps. And so because of that, each step is a prescribed speed. There's no in between. Now, there are other options. You can get an Arduino driver or other things that have much finer speed control than this, at which point you would be able to dial this in a whole lot closer. But at that point, we're adding more complication. We're adding more skill set required to do programming and other things. We're also adding more expense. So for the budget-friendly option, this is what people are using. And so that is what the test was. So we started at 323, and initially it dropped to 312, but then it went back up. So there's clearly components in here that are designed to smooth out the load. Like it senses a load and it increases to compensate. And so we had a range between 312 and actually 340. So it ended up driving it, while it was cutting, a little bit faster than what we started at. And I actually had a similar result at the other speeds that I don't have film footage for, where it would actually speed up a little more than where we started. At 603, we dropped to 595, so only an 8 RPM drop. So that's fantastic. And at 908, we only dropped to 893, so a 15 RPM drop. So one thing that this has that other units don't have is that little connector right there in the corner. Now that is for a tack. In other words, little magnet, little hall sensor type unit that a lot of treadmills come with. And that will help dial in the speed maintaining components on this. If you want to hook that up, if we were to hook that up to the mill and do the same test, I bet it would work even better as staying close to that starting RPM. But again, at that point, we are adding more complication. Now, that may be good complication. That may be something that is worth having. But for the purpose of this test, I wanted to keep it simple. This performed the best and not the best at the same time, because the fact that it actually ended up going faster, that might be a little bit of a bad thing. So overall, it shows that this is designed for a treadmill. That's what it's for. And if you repurpose it to run a mill or a lathe or a bandsaw, you're still dealing with something that was designed for a treadmill. And if you don't do things like a little more advanced signal generator or hooking up the magnetic sensor for speed, it's not going to perform quite the same as the other units do. So what does it all mean? What's the result? Which one of these units is best? Well, I came in with my own bias. Very fond of this. Was fairly impressed with the testing I did with this. Not so impressed with this. And that was my opinion before any of this testing happened. I then took the results that I've shared with you as far as the RPM drop. I also took other characteristics of these units and I put together 7 categories and then ranked them all 1 through 3, 1 being the least of the 3 and 3 being the best of the 3, and then I summed them up. And I thought we would have a clear, decisive first, second, and third. But actually what I ended up with was 14 points for this, 13 points for this, and 14 points for that. So that to me is a wash. That means that depending on your specific needs, any one of these is a viable, inexpensive option. And when I say inexpensive, under $100 to power a treadmill motor. So my 7 characteristics were clean power, robustness, speed adjustment, cost, speed drop, so how torque relates on your machine, size, and actually something that you didn't see me test in the video, which was minimum speed. Depending on what you're hooking this up to, if it's a tumbler or something that requires a super slow speed, minimum speed might be important. So I went ahead and threw that in. Here's the results. For clean power, the Variac wins, hands down. It's super clean, ran super smooth, very happy with how it functioned. The MC-2100 comes in second. It's got pretty good, fairly clean power. And the SCR voltage controller's power is by far the dirtiest. Robustness, again, the variable transformer gets the win because there's almost no components here. Yes, there's a bunch of components here on the face, but they have little to do with this. Everything else is just going to work based on mechanics, not components. Because this is a coil of wire with a terminal going to different coils of wire and creating different volts, there's not a lot here to break unless you overrun this. In other words, you drive it too hard, you pull too many amps through it, and you burn up your coil wire or something along those lines. But that's what the fuse is for. So as far as robustness, this is extremely robust. This guy right here, I'm extremely happy with this. Very few components. I've been using these in a shop environment for a couple of years now, as long as you get the good one, not the crappy long skinny one that everyone seems to buy because it's cheaper. Get the good one, and they perform extremely well. This guy is not as robust. I was playing with one of these and I brought it up to a fairly high RPM. I turned it off. I turned it back on. The board quit working. I blew up some of the components on it. It is just not as robust. Now, obviously, a lot of people aren't going to be turning it up to max RPM and then turning it on. That was an extreme situation, but there are a lot of components to fail here. And so that's why it comes in third for robustness. Speed adjustment. This guy right here. With a coarse speed and fine speed potentiometer, you can dial this in exactly where you want it. This guy right here, you can get it pretty close. This guy, unless you do something more advanced, not so close. Cost. This one was a little harder to do. The MC-2100 came in first, but that's only if this comes in your treadmill. To buy this unit is about $100. To buy this is $13. For this to be the number one for cost, you have to assume that you got one of these in your treadmill. So if you paid for the treadmill, you bought it for the motor, the board came for free. At that point, we're looking at $13. This guy, it's about $30 for the unit, and you are looking at another $13, $14 for the bridge rectifier. Get the good one, not the one I show in the bench tests. If you're going to be using it for any length of time, you want the heavy-duty good one. And then you do need some power cleaning things, such as chokes and such. And to get those used for about $25. So we're looking $60, $70. That's assuming that your treadmill didn't come with a choke. If it came with a choke, you're sitting right around $45. That's why this one comes in second. This guy, you're looking at about $70, depending on which one you get. And then you still have to have the bridge rectifier. So that's another $15 on top of that. So this guy right here is definitely the most expensive of the three. As far as loss in torque, in other words, the check for speed, I gave these two a tie and gave them 2 points. Now, this one in some ways performed better. The fact that it didn't drop as much, but also the fact that it sped up and was a little inconsistent. You know, if you don't know what it's going to do, you can't plan for it. If I know this is going to drop 20 RPMs every time I make a cut, and I want to make a cut at 600 RPMs, I set it at 620. This guy right here, you put it at 6, it may fluctuate around. So these two tied for second. Nobody got first. And this one came in last because it had 40 to 50 RPM drop. So you have the least amount of torque. but still an amount that can easily be adjusted to overcome. You know, again, you want it to be at 600 RPM, you know you're going to lose 40 to 50, you set it for 650. That is reasonable. I would feel very comfortable using this in a situation where I needed a specific RPM because I know consistently what it's going to do. Size. This one wins hands down. It's actually a lot smaller than the package here if you take it out of this enclosure. And you can easily store an extra one. This is my extra one. You can easily put it in a box like the satellite box you see on my bench next to my mill. It's easy to place inside an enclosure. It's the smallest. This guy is definitely usable. You can easily find an enclosure that it can fit in, but a little bigger, and the interface is a little chunky. And by comparison, this guy's huge. The other factor with this one is you have to put it somewhere where you can get to this knob, because you can't easily remove this knob and have it be remote. Yes, you could use a servo like was suggested in one of the comments on my variable transformer video. But again, we're adding more cost and more complications. So for the budget, easy, this has either got to be on the bench or under the bench so that you can get to this knob. And then the last part was minimum speed. The variable transformer had the best results for minimum speed. I was able on the mill to take this down to about 18 RPMs, which super slow. Depending on your project, that may be an option for you. The MC-2100 came in second, and it had minimum speed of 65, still pretty slow. That's the best I could get. Couldn't get any slower than that. If you needed to, of course, you could gear any of these to get down to the desired RPM. But 65 was still pretty good. And then the SCR was about 150. Definitely on the low end, you know, you're not going to have the same slowness with this. Now, what does all this mean? What do I do with this lovely list that I've put together with all these points about these three different things? Well, you take the ones that are important to you. If clean power, cost, and minimum speed are important to you, then you add up the score and find out which one's best. And that's the one you get. If robustness, less loss of torque, and say maybe ability to adjust the speed is the important factor, you add those together and figure out which one's best. The reality is, and I totally did not expect this is a wash. For most applications out there, you can hook up any one of these three units and be happy with it. All I can say is figure out what's important to you. Look at what parts came in your treadmill. Look at what your budget is. Decide which one you want and go with that one. I don't think you'll be dissatisfied with any of them.
If you like what you've seen, please click like. If you'd like to see more, please subscribe. Thanks for watching.